I am Rajan Chakrabarty from Washington University in St. Louis. I missed yesterday's session because of some mandatory community service, but now I am happy to be here. This is our first year progress report. So the title was changed from the original title of our project, but just to give the crowd here, I also see a lot of new faces. This is the original project which was funded by this program, which is first principles physicochemical characterization of two stratospheric aerosol injection candidates, alumina and calcite particles. By first principles, we imply to understand the spectral index of refraction from the visible all the way through IR, using photoacoustic spectroscopy and electron energy loss spectroscopy. And the approach we want to take is a bottom-up approach, atomic scale through particle scale. And then there is also the chemistry side, which is in collaboration with Lu Xu, who is a chemist who is trying to mimic the stratospheric chemistry in the lab using flow tube reactors. For the electron energy loss spectroscopy, I'm partnering with Professor Rohan Mishra from the Material Science Department. He's an expert in microscopy and modeling. So this is the team, and also each of us, we have our students who are also here, and I'll be acknowledging them throughout the talk. So this is the brief outline of our talk. First, I want to make a case, why is alumina important? This is relevant because you have heard a lot about diamond, but alumina is equally important, so let's hear why. Then I'll talk about this curious case of missing shortwave absorption spectra for alumina, and how it pertains to the problem we are trying to tackle here. Experiments we have done the first year to unveil the missing spectra, results, and implications for broadband albedo, courtesy Paul. He asked me during the November meeting to look into this. So alumina, why is it important? Aside from SAI, alumina is already there in the stratosphere. This is abundant, and specifically we are expecting that this is going to be more abundant as we go with this crazy mega constellation era space race. And just to give you a perspective, when a 250 kilogram satellite re-enters into the environment to Earth, it emits around 30 kilogram of alumina particles, and they endure in the stratosphere for decades. And just in 2022 alone, we had around 2 gigagrams of alumina nanoparticles from satellite launches and re-entry suspended in the stratosphere. So this is a big problem. The other thing is the community, the modeling community has well established that alumina could be a potential Psi candidate. And this is primarily because of its efficient shortwave scatterer, negligible shortwave absorption, relative low density, and well understood environmental toxicity. So this is the conventional understanding we have. And this is Sandro has been publishing a lot of work. This is a graph from one of his 2024 paper where essentially he compares the tug of war between relative forcing and temperature anomaly for all the possible candidates, sulfate, all the solid nanoparticles are below the sulfate line, which is the perforated line. But the community also has some caveats, meaning that the complex index of refraction is not well understood. Particle size and particle shape could affect the relative forcing, but we do not know how much and to what extent. The big elephant in the room, as we see it, is the complex index of refraction, the spectral. How much do we know about it for the alumina? And if you look at the current state of knowledge, you see that in the short wave, you have a real index of refraction of around 1.7 and the imaginary around 10 to the power minus 7, which has been input into all the climate modeling work, or stratospheric modeling work to investigate this radiative forcing versus temperature anomaly. This was based off of John's work in 2016, which is idealistic, meaning that, as you can see, 10 to the power minus 7 implies negligible absorption across shortwave. It is ideal alumina with no surface defects, that is the color center defects, or any vacancy defects. So these sort of assumptions sort of defies the second law of thermodynamics, where entropy actually favors defects in any material. So the question is, can you have a material with no defects and have such a index of refraction and then do your calculations? So we want to investigate that. And the root of the problem, if you look under the hood, is this whole genesis of it is in this handbook of 1998, where you had all the data sets corresponding to the index of refraction calculated by different groups, compiled, and you can see here that this index of refraction here, there is a drop right around 200 nanometers for K in the handbook, and we do not know if this is an instrument artifact or actually the authors measured this, and then it again starts around the IR region. And so this is the missing portion, which John did a pretty good job, at least of bridging it using theory. So we wanted to investigate if this is accurate. If not, what could be the actual values and what is the implications of it. So the approach we use is, on the particle scale, we use photoacoustic spectroscopy, essentially photons. Then with Rohan Mishra's expertise, we use scanning transmission electron microscopy coupled to the EELS spectroscopy for single particle. And then we also use density functional theory to make sense of what we see. So density functional theory is essentially a quantum mechanical atomistic simulation model coupled to the non-equilibrium Green's function to give you pretty much the entire different material properties. So photoacoustic spectrometers, this is something which has been there for the past 100 years, or actually more than that, for 2 decades now. But applied to aerosols, it has only gained prominence since the 90s, late 90s. And here, what essentially this spectrometer does is that any material, any particle which absorbs light will re-emit it back as heat. This heat emission is essentially a pressure change in the surrounding atmosphere. So now if we pulse a laser at a particular frequency and we put a microphone next to the particle of interest, also synced at that particular frequency, we can hear the pressure differences, which is essentially sound waves. So essentially we are making particles sing if there is an absorption component. My lab is a big fan of open source, so graduate student Prabhav, he's a third year student. We have, as part of this grant last year, we published this tutorial for the community. If you want to build yours, everything it's like a 30-page paper, how to build one of the photoacoustic spectrometers in the lab, including parts list. So please check it out. So this is some, one of the custom built ones in my lab. We built 5 of these for this project. Not that all of them were working for all the but nonetheless did the job. Next, what we do is, with the absorption and scattering cross-sections, what we get, we also have a scattering cross-section module. We use this PyMeScat inversion package, which is now a well-established package developed by my group in the atmospheric science community as well as in the astrophysics community, to get a imaginary and a real part of index of refraction for the particle size distribution. So this is one technique for ensemble as a function of particle size. How do we get the index of refraction? This is essentially the schematic of the photoacoustic experiments in the lab. You have a particle shaker, which is a version adapted off of Faye McNeil's group by Dhruv Mitru, who was a previous student of Faye's dust generator, and essentially you have this bunch of instruments along with the photoacoustic spectrometer connected. And just to give you too many clickers. So this is the lab view. You can see the experiment. This is a dust shaker. You can see it is kind of generating different size particles depending on the frequency of shaking. And these are the photoacoustic spectrometers running simultaneously, all of them, measuring the absorption and scattering cross sections in 1 second resolution, and the sizers simultaneously measuring the size of the particles, generating. So this is a. So what did we find? We ran statistically significant. This I give a lot of credit to my students and postdoc Taveen. They ran 35 different runs after the November meeting. And what we found was that different polymorphs of alumina did not really matter when it came to the imaginary part of index of refraction. Even the morphology also did not, of course, be corrected for the irregular shapes. And the index of refraction ranged from around 10 to the power minus 3 to 10 to the power minus 4 across the 375 to 1047 visible wavelength, which is around 3 to 4 orders magnitude higher. So this result was, we wanted to verify it with another technique, which is where, and these are the shapes of the particles, what we say from perfect spheres to irregular shape, porous shapes, what you find. And these were all particles brought from US Nano. They claim 99.9% pure alumina. And so we did check the particles under the microscope. This was Rohan Mishra's student, Jian, in Oak Ridge National Lab using their state-of-the-art microscope. And this essentially, the STEM electron microscopy is, you look at the inelastic scattering by the electrons as they pass through the sample in the low loss electron volts, which is less than 50 eV. And that gives you information on the phonon's optical excitation plasmon, whereas greater than 50 eV, whatever spectra you get of the loss, you get information of the oxidation state, bonding mechanism, and chemistry. So we send the samples there, they analyzed it, and this is the consolidated imaginary index, what we find. So the thing to note here is that this blue line here is what our present, maybe I should just, the present understanding is. The handbook did get the band edge gap correctly, close, at around 8 to 10, around 9 eV, and then it dropped, and this was bridged by John Daikima. But what was missed out was that there is an oxygen vacancy defect which showed up at around 5.5 eV. And then you see that this Urbach tail, you extend it, and you find a 3 to 4 orders magnitude of increase in imaginary refractive index. So why increase in imaginary index? You have John Kevin actually doing DFT calculations, and what happens is that you cannot ignore oxygen vacancy defects in alumina. What this means, because they're very low formation energy and are expected in high concentrations in any material. Even you do the highest, most purified form of synthesis. And they result in dangling bonds. So these dangling bonds, the moment you have electrons coming in, there is a change in their electronic states, and it happens at around 6 eV, right, where we see this dip. So this is work in progress. Then on the particle scale, we wanted to see the implications. So with our present understanding of John's and this study, what it shows is that on the particle scale for different size distributions, depending on the wavelength and the size, median diameter, you can see almost a 3-order magnitude enhancement in absorption cross sections. I should say coefficients. And then what about sulfate coating? These particles could be coated. This is a well-known phenomena in the aerosol community, that the moment you coat an absorbing particle with something which is transparent, in this case sulfate or organics, you are going to see an enhancement in the absorption cross-section, which we call it as a lensing effect. And so upon coating, you find that the absorption enhances by a factor of 1.5. So that imaginary index will further go up upon coating. Finally, broadband albedo. This is work done by actually a first-year student, very talented, Mars Zhang, who is also here, and Taveen. I don't know, Taveen, he did a lot of work. He's a postdoc. His photo did not show up in my presentation. I'm sorry. I put it actually, but I don't know where. Maybe things got... I don't want to make him angry because, you know, it's going to bite me back. So this is a broadband albedo calculation for different distributions. And this is similar to the bond albedo. I think this concept was presented yesterday. I was not here. But this bond albedo paper by Francis Pope, actually, if you look at the way they calculated, is not there, you know, it's not the exact bond albedo. So what it is like, if you were to coat a layer of these particles on the stratosphere, what is the change in the albedo across the short wave, which is the radiative forcing essentially. And so this is a function of size. As the size increases and the number concentration of the particles from 8 to 24 kilometers in the stratosphere, you can see that the perforated line is the present understanding. This is the current index of refraction. The albedo drops. It is more significant for higher sizes and greater concentration, particle number concentration. Now you might say that this is insignificant, but the albedo, broadband albedo change of 0.018 can counter the entire global warming effect from greenhouse gases. That sensitive it is. So this is what we find. And the other important thing what we find is that under the present understanding of alumina, if you have an atmosphere which is cloud-free, clear sky with no aerosols, just the baseline, the moment you seed the atmosphere with, seed the stratosphere with aerosol, with alumina with 10 to the power minus 7 imaginary index, is almost always going to give you an enhancement in albedo, which is what you want. But if you use the values from this study, you see that there is a break-even surface albedo, meaning that greater than 0.71, these particles are going to have a net warming effect. This is very important because all roads end to the poles. Whatever is there in the stratosphere will eventually end up in the poles. So over sea ice and snow, this could have actually a negative effect, which gives rise to snow melt. So this is something which we are investigating right now. So going forward, in 2 weeks, we should have the entire spectra, not only just in the short wave, but up to 62 micrometer, the IR index of refraction spectra too. The short wave spectra, whatever we have shared with Simone's group as well as Faye McNeil's group. I'm open to sharing with anyone. I think I already made connection here with Sandro. We'll be sharing, and if anyone wants to send me an email. We are looking at the role of aggregation in aerosol absorption enhancement. So if these particles were to aggregate, what would happen? And then there is experiments going on by Yuan, who is a new postdoc in Lu Shu's group, to look at the gaseous species uptake by alumina aerosols. So this is something you can expect to see in year 2 progress report. That's it for now. Thank you.